In Chapter 7, single-dimensional arrays are presented. Suppose that we want to read in 100 numbers, compute their average, and determine how many numbers are above the mean average. With the tools that we currently have in our toolbox, we would have to declare 100 variables, repeatedly writing almost identical code 100 times. This is inefficient and impractical. Suppose we wanted to read in the number of data items from the user and then perform the previously mentioned task. We would have no way to do this. We obviously need a new tool for our toolbox, one that provides an efficient and organized approach. If we consider the problem a little deeper, we will notice that we have a fixed number of data elements and they are all of the same type. This observation is vital. The solution to our dilemma is an array. An array is a data structure that stores a fixed size sequential collection of data elements of the same type. Once an array is created, the size of the array is static, that is fixed, and all data elements in the array must be of the same data type. An array reference variable is used to access the elements in the array using an index. You may recall that this is similar to the string data type. Hold that thought. We will have more on that topic later. Like other data types, to use an array in our program, it must first be declared. This is done by declaring a variable to reference the array and specifying the type of data that the array will hold. The syntax is shown on the slide. We begin with the data type, followed by a pair of square brackets that signify an array of the stated type, followed by the array reference variable name. Thus, an array is a collection of a fixed number of data items of the same type. It is important to note that this does not create the array, but only creates the variable that references the array. That is, the array reference variable holds the address of the array, but not the array items themselves. An array is not a primitive data type like int or double, char or boolean, etc., but rather a reference type. This is vitally important and will have serious implications moving forward. If declaring the array reference variable doesn't create the array, that is, allocate space in memory to hold the contents of the array, the pressing question is, well, how do we create the array? And I'm glad you asked. We will create the array with the keyword new. We assign its reference to the array reference variable and give it a fixed size, which can never be changed. The syntax is shown in the slide. Well, by now you know that programmers like succinct code, and that means we want to be able to declare and create our array in a single line of code. And indeed that's possible, and exactly how we will handle this moving forward. The syntax for such is indicated on the slide. You will notice that it is vital that the keyword new appear in this single statement to declare and create the array, and also that we give the array its fixed size in the brackets on the right-hand side of the assignment statement. It is worthwhile to state that when an array is created, the elements of the array are assigned default values based on the type of elements that the array will hold. The default values for the various data types are listed on the slide. When we want to access or refer to elements in an array, we must use an indexed variable, which consists of the name of the array, a pair of square brackets, and the index of the item. It is important to note that arrays are zero-based. That is to say, the index of the first element in an array is 0, and the index of the last element in an array is length minus 1. We can use indexed variables in the same way that we use any other variable. As an example, consider that we wish to sum the contents of mylist sub 0 and mylist sub 1 and store the result in mylist sub 2. The statement to do just that is shown on the slide. Since an array is a static data structure, its size is fixed. Once the array is created, the size cannot be changed. We are able to capitalize on this knowledge and use the syntax shown on the slide to determine the length of the array. That is, to determine how many items are in the array. Thus, for an array named mylist, there are mylist.length data items, or items in mylist. At this point, it's worth noting that length is not a method, therefore it does not have parentheses. Also, it bears repeating that the index of the last item in mylist is mylist.length minus 1. As we have seen with other variables, there is a shorthand notation to declare, create, and initialize an array in a single step. The statement shown in the slide declares mylist to be an array of type double and size 4 and initializes the elements of the array to the data items included in the curly braces. Hence, mylist sub 0 is initialized to 1.9, mylist sub 1 is initialized to 2.9, mylist sub 2 is initialized to 3.4, and mylist sub 3 is initialized to 3.5. So mylist has a length of 4, the index of the first element in mylist is 0, and the index of the last element in mylist is mylist.length minus 1, or 4 minus 1, which is of course 3. You will notice that the keyword new is not necessary. It's also important to note that this is the only way we can create an array without using the keyword new. In this slide, you will see that the shorthand notation saves quite a few lines of code. If we did not use the shorthand notation in this example, we would have to explicitly assign values to each element of the array in a single statement, after first declaring and creating the array. Just a word of caution. If you use the shorthand notation, it must appear as one single statement. It cannot be broken into two statements. When we process an array, a for loop is ideal because all of the elements in an array are of the same type and the size of the array is static. So we know in advance, or can easily ascertain, the number of elements in the array as well as the index of the last element of the array. You will recall the syntax of the for loop as shown in the slide. We will now look at some essential operations in array processing. Assume the declaration and creation of an array named mylist of type double and size 10 for all the examples. Before we can consider performing any type of operations on the elements of an array, it must first be initialized. We have already seen how to hard code in initial values, but now we will consider the situation where the user will input initial values. Of course, this means that we must enlist the use of a scanner to read in the user input. We use the for loop to access each element in the array. The loop counter I is used to reference the indices of each and every element in the array. You will remember that we said that the index of the first element in the array is 0, so we use I equals 0 as our initial value. Because mylist.length minus 1 is the index of the last element, we use I less than mylist.length as our continuation condition for our loop. Notice that we're using the sharp inequality for the loop continuation condition. The loop body consists of a single statement that reads in a double from the user and assigns it to the array element at index I. For our example, mylist.length is equal to 10, so our loop will iterate 10 times, beginning at I equals 0 and the last iteration occurring when I equals 9. Thus, we will assign the user-designated values to mylist sub 0, mylist sub 1, mylist sub 2, etc., all the way through and including mylist sub 9. It's worthwhile noting that while there are 10 values in our array, there is no mylist sub 10. This is because, once again, the first element in my list has an index of 0. Another possibility is to initialize the array with random values. Since there is no user input, we do not need the scanner. In any array processing, we utilize a for loop, and in this case, the body of the for loop has only a single statement that assigns a random double from 0 to 100, not including 100, to the items in my list. Another important operation is to print the contents of the array. Again, we use the for loop, and this time the single statement in the body of the for loop is a print statement. Note that as coded, we print each and every element in the array because we start at I equals 0 and end with the index of the last element of the array. Consider the case where you only want to print a subset of the array. How would you adjust the for loop to print only the first 5 elements of the array? Summing the elements of an array builds on a concept that we have seen before. To sum an array, we must first initialize a variable to hold the sum. Here we call it total, and we initialize it to 0. Again, we use our friend the for loop to run through the indices and sum the elements in the array. Finding the largest element in the array requires that we declare a variable, let's call it max, of the same type as the elements in the array. We initialize max to the value in the first element of the array, and then we step through each element in the array, starting at mylist sub 1, and compare the value in that element to max. If an element is greater than max, then we assign that value to max. Once we have considered every element in the array, max will hold the maximum value. Can you modify this code to find the smallest element in the array? Another operation that we need to understand is random shuffling of the array. Please watch the video note in your online textbook resources for an in-depth discussion of how to randomly shuffle or reorder the elements of an array. Pay particular attention to the way math.random is used to generate a random index to determine which element to swap with the current array element. Also notice how the swap is performed. If you struggled with the concept of swapping previously, please take time to review and be certain that you have a full understanding of how to swap two variables. Sometimes you may want to shift the elements in an array to the left or to the right. In this example, the elements are shifted one position to the left, and the first element is shifted to the last element of the array. We begin by creating a temporary variable to hold the value of the first element in the array. This is necessary because when we begin shuffling, we overwrite the value in the first element, mylist sub 0. If we have not previously held on to that value, the value of mylist sub 0, in some temporary variable, the data will be lost when we shift mylist sub 1 into mylist sub 0. Again, you notice that we use the for loop, but we set our initial value to 1. After the for loop is terminated, the element in mylist sub 1 through mylist sub length minus 1 have been shifted one position to the left. And all that is left to do is to assign the value in temp into the last element in that array, mylist sub length minus 1. We will now trace an example program that uses an array. An array is declared and created. The name of the array reference variable is values. Values contains the address of the first element in the array. Values sub 0 is the first element in the array. And values sub 4 is the last element in the array. Because the array is of type integer, a numeric data type, all of the elements of values are initialized to 0. Values is not equal to 0, however. Values is the array reference variable, and it is equal to the address of the first element in the array. Specifically, values holds the address of value sub 0. We begin the for loop and create an integer variable named I and initialize it to 1. The loop continuation condition evaluates to true, so the loop proceeds. Value sub 1 is assigned the value 1 plus value sub 0, so 1 is stored in value sub 1. The after iteration statement is executed and I is incremented. 2 is now stored in the memory location referred to as I. The loop continuation condition evaluates to true and the loop continues. Value sub 2 is assigned the value 3. I is incremented, and now I is equal to 3. The loop continuation condition evaluates to true, and the loop continues. Value sub 3 is assigned the value 6. I gets incremented to 4. The loop continuation condition is true. And value sub 4 gets assigned the value 10. I is incremented to 5. The loop continuation condition now evaluates to false, and the loop is terminated. The statement immediately following the loop is executed and value sub 0 is assigned the value 11. An enhanced for loop, called a for each loop, is available to traverse the array sequentially without using an index variable. Note that when traversing the array MyList, the variable value must be declared as the same type as the elements in MyList. If you need to traverse the list in a different order or change the elements of the array, as in shuffling, you would need to use a standard for loop and an index variable. Please refer to your textbook online resources to view the code and simulation for Case Study 7.3, Analyze Numbers. This case study finds the number of items above the average of all the items in the array. The user enters the number of items in the array and then enters the values for those items. Note the code that creates the array and pay particular attention to how the user-defined size is used to create the array. Also notice that a single for loop is used to both input the values from the user and sum them. The average is then computed and another for loop is used to count the number of array elements above the average. Please watch the video note in your online textbook resources that discusses the deck of cards case study in section 7.4. Notice that 3 arrays are used: deck, suits, and rank. Observe how the arrays suits and ranks are declared, created, and initialized in a single statement. Further notice that 3 separate for loops are used to first initialize the cards, then shuffle the cards, and finally display the first 4 cards. Why is the integer division operator used to determine the index for the suit and the remainder operator used to determine the index for the rank? Here's a hint. What is the largest possible value in dexibi? What is that value, div 13, and how many elements are in the array suits? Can you see how this will result in an index that is legal for the array suits? And this is similar for ranks. Now let's consider the problem of copying arrays. Let's propose that we need to copy the contents of one array, say list 1, into the contents of another array, say list 2. So our first inclination might be to simply use the assignment operator, the equal sign, but this is a logical error. This will not result in a syntax error, so we may think everything is just fine, but don't be fooled. Things are far from fine. Remember that list 1 and list 2 only hold the addresses of the first element in the array, not the contents of the array itself. When we use the equal sign in this way, we have copied the address of list 1 into list 2. So essentially, we have given list 2 access to the contents of list 1. We have not made a copy at all. So what is the solution? Whenever we want to duplicate an array or copy the contents of one array into another array, we must copy the array's individual elements into the other array. We use a for loop to copy the elements one by one from the source array, in this case list 1, into the target array, in this case list 2. Note that the target array must be declared and created and must be at least the same size as the source array that we are duplicating. Another solution is to use the array copy utility. At this point, you should recognize array copy as a method in the system class. To use array copy, the target array must already be created. We invoke the array copy method as system.arrayCopy and pass 5 parameters. The first parameter is the name of the source array, so list 1. The second parameter is the starting position in the source array, where the copy is to begin, so 0. The third parameter is the name of the target array, so list 2. And the fourth parameter is the starting position of the target array, so 0. And finally, the fifth parameter is the number of items to be copied, so list1.length. Just like we can pass primitive data types to methods as parameters, we can also pass an entire array to a method as a parameter. Because an array is not a primitive data type, we are passing the reference of the array, that is the address of the first element of the array, to the method. This is a very important distinction. You will recall that primitive data types are passed by value. Arrays, however, are not a primitive data type and are in fact not passed by value, but rather passed by reference. This means that if you change the array in the called method, it will also be changed in the calling method. It is crucial that we fully comprehend the difference between passed by value and passed by reference. Parameters of primitive data types, that is int, char, boolean, double, etc., are passed by value. A copy of the value of the variable is made and a new memory is allocated to hold that value. When the value changes, only the copy is changed. Therefore, changing the value of the local parameter inside the called method does not change the value of the variable in the calling method. Parameters of array type, however, are passed by reference. This means the reference or address of the array is passed. Thus, when a variable is created to hold the address in the called program, the array itself is not copied, only the address. The address is the key to accessing the elements of the original array. So any changes made to the array in the called method affect the original array. Consider this simple example. You will notice that since x is a primitive data type, even though the corresponding parameter number is changed in the method m, the value of x is not changed in main. The situation is different with y, however. Since y is an array, when y is passed to m and the corresponding local parameter, the array numbers, is changed in m, the original array y is also changed when control returns to the main method. Please refer to your online textbook resources for a complete listing 7.3 for a further example of pass by value versus pass by reference. Just as we can return primitive data types from a method, we can also return an array from a method. But as you might suspect, there's a very important distinction. When we return an array, we return the reference to the array. Again, that is to say, we return the address of the first element of the array. In this example, the address of an array we called list in the method reverse is passed in. A new array called result is created in the method and returned to the calling program. So let's consider the trace of this method reverse. Let's assume that the first 2 statements on the slide appear in the main method. List 1 is declared to be an array of integers, created and initialized to the values in the curly braces. List 2 is then declared and invokes the method reverse, passing list1 as an actual parameter. Upon invocation, list1 is mapped to the formal parameter list. That is to say, the address of list1 is now stored in a new variable named list that is local to reverse. Next, an array named result is created, which has the same size as the array list. A for loop is used to iterate through the indices of both list and result simultaneously. Two variables are declared in the initial action of the for loop. I has an initial value of 0 and will be used as the index of list. J has an initial value of result.length minus 1, that is the index of the last element in result, and will be used as the index of result. The loop continuation condition is I less than list.length. That is, as long as I, the index of list, is within the legal range of list, the loop will continue. Finally, as an after iteration action, I is incremented and J is decremented. Do you know why? I suggest that you stop the video and ponder this and restart the video when you think you have it. Okay, here is why we increment I and decrement J. In order to store the reverse of a list in result, we need to put the value of the first element in list into the last element of result. Then we need to put the value of the second element of list into the second to last element of result. So we start at list sub 0 and assign that value to result sub 5. Then we assign list sub 1 to result sub 4, and so on. You'll notice that the indices are increasing on list while simultaneously decreasing on result. Therefore, we need two variables, in our case I and J, to represent the indices of the two arrays. Additionally, we need to increment I at the same time decrementing J. Here, I equals 0, and our expression evaluates to true, so the loop continues. The value in list sub 0 is assigned into result sub 5. I gets incremented and J gets decremented, so I equal 1 and J equals 4. The loop continuation condition evaluates to true, and the loop continues. The value in list sub 1 gets assigned into result sub 4. I gets incremented to 2 and J gets decremented to 3. The loop continues until I equals 6. At this point, I less than 6 evaluates to false, and the loop terminates. The reference to result is returned to the calling method, which stores it in the array reference variable list2. List1 remains unchanged, and list2 contains the reverse of list1. Consider case study 7.8 that presents the program count letters in array, which counts the occurrences of each letter in an array of characters named chars and stores those counts in an array called counts. Counts has a size of 26, where counts sub 0 represents the number of A's, counts sub 1 the number of B's, etc., and finally counts sub 25 is the number of Z's. The array chars is initialized by randomly generating 100 lowercase letters, thus it has a size of 100, and utilizes the random character class presented in listing 610. Notice the simplicity of the main method and realize this is because the details utilize the concept of modularization by encapsulating the code for each specific task in a method, thereby making the main method straightforward and easy to read and understand the logic. Consider each method and identify the method header, method signature, and return value type. Further, identify the number of parameters required of each method and whether each parameter is passed by value or passed by reference. Finally, drill down into the body of each method to understand the logic and implementation. Notice how the for loops are used and specifically the detail of the for loop header. Consider the code on lines 37 through 42 and lines 60 through 64. Can you identify what this code is doing? If not, refer back to your notes from Chapter 5. Lastly, study the code in lines 51 to 52 to determine how this code accurately increases the count of a given character. Java allows us to pass a variable number of arguments of the same type to a method. The syntax for this in the method definition is type name followed by an ellipsis followed by the formal parameter name. It is important to note that only one variable length parameter may be specified in a method, and this parameter must be the last one in the parameter list. This is possible because Java treats variable length parameters as an array. It is equally important to note that a return value type cannot be a variable type parameter. See listing 7.5 in your online textbook in section 7.9 for an example program. In addition to the previously presented common operations that we perform on arrays, the concept of searching an array for a specific data element is paramount. There are many algorithms and many data structures devoted to searching and the optimization of such. As you progress through the curriculum, you will not only learn the various search algorithms, but also how to determine the efficiency of an algorithm. As an introductory course, we will only consider two basic search algorithms: linear search and binary search. First, we consider a most basic search algorithm, the linear search. In a linear search, a key element, the element we are searching for, is compared sequentially with each element in the array until one of two things occur. Either the key is found and the index of the element that matches the key is returned, or the list is exhausted without a match being found and a -1 is returned. Why do you suppose that -1 is returned and not 0? It is important to understand that to use a linear search, the elements in the array can be in any order, since in an average case we will have to search through half of the elements in the array to find the key, and the execution time increases linearly as the number of array elements increases. This is a very inefficient search algorithm for large arrays. Please refer to listing 7.6 in section 710 of the online textbook resources for the implementation of the linear search method. Next, we consider another common search algorithm that is a bit more efficient than linear search, the binary search. The efficiency of the binary search algorithm hinges on the constraint that in order to use binary search, the contents of the array must be sorted in either ascending or descending order. The search for the key element begins at the middle element in the array, thereby dividing the array into two parts. The first half, below the middle element, in which all items are less than the middle element, and the second half, in which all elements are greater than the middle element. The key is compared to this middle element. If the key is less than this element, we continue the search in the first half of the array and disregard all of the elements in the second half. If the key is equal to the middle element, the search ends with a match and the index of that element is returned. If the key is greater than the middle element, the search continues in the top half and the elements of the bottom half are disregarded. This process continues until the key is found and the index of the matching element is returned, or the search is exhausted and the key item is not found. Upon completion of the binary search, two options exist. Either an element in the array matches the key, or no element in the array matches the key. When an element is found that matches the key, the index of that element is returned, just as in linear search. However, when no element is found that matches the key, the binary search does not return 0 or -1. Instead, the return value gives information to the user as to where the item should be inserted in the list. That is to say, negative insertion point -1 is returned. Can you see a reason as to why the negative insertion point -1 is returned and not just the negative insertion point? What if 0 were the insertion point? If negative insertion point were returned, -0 or 0 would be returned. Was the element found at 0 or was it not found and needs to be inserted at 0? This is ambiguous, and so we can see that it's necessary to return negative insertion point -1. Sorting is another common task in programming. You can see from the previous examples of searching that one important benefit of sorting is improved search algorithms. There are indeed several sorting algorithms, but for the scope of this class, we'll introduce only selection sort, an intuitive sorting algorithm. The implementation of selection sort can be found in listing 7.8 of section 7.11 in your online textbook resources, along with an accompanying video note that details selection sort. Please watch this video note and code along to gain an understanding of the selection sort. You will learn that selection sort first searches the array for the smallest number and swaps it with the first element in the array. This assures that the first element in the array is in the correct position and no longer needs to be considered. Next, the remaining elements are searched for the smallest element, and the smallest element is swapped with the second element in the array. This continues until there is only a single element in the array in the last position, which we conclude is the largest element and in the correct position, and so the sort is completed. The java.util library contains a class named Arrays that contains many useful methods for common array operations, such as sorting, searching, comparing arrays, filling array elements, and returning a string representation of the contents of the array. You can use the method sort to sort the elements of an entire array or a partial array. Use the binary search method to search for a specific value called the key in a pre-sorted array. The method equals determines if two given arrays have identical elements in corresponding positions and returns the resulting Boolean value, true if they are identical or false otherwise. The method fill can be used to fill all or part of an array with a single initial value. The toString method is a useful way to return a string that represents all of the elements in the array. At this point, it is worthwhile to point out that the main method is just a regular method. It can be called from other methods and has one formal parameter whose type is an array of strings. Therefore, you can pass arguments to the main method in a method call. The example on this slide demonstrates how the main method in class B is invoked by the main method in class A. The application of this is beyond the scope of this class, but it bears introduction.